We've solved a homogeneous linear system where the lambdas were real and distinct, but the lambdas, the eigenvalues, can also be complex valued. As an example of this, let's take a look at the homogeneous system x prime equals ax, and here our matrix is 0, -9, 1, and 0. So as before, we are going to let the x equal to some e to the lambda t times v, where this is a non-zero vector. The definition of an eigenvector requires it to be non-zero. We are looking for non-trivial solutions. So all of those things are consistent, and they want us to have non-zero constant vectors. When we sub this in, what will happen is that we will end up getting a minus lambda I v equals 0. So this is an eigenvalue problem. Now, as before, number one, we need this matrix to be non-invertible so we can find non-trivial solutions. So what we need to do is solve determinant a minus lambda I equals 0. This is going to give us what's called the characteristic equation for lambda. It's going to be a polynomial whose degree is the same as the order of, or the size of our system. A minus lambda I in this case is going to be negative lambda, or I should say the determinant will be negative lambda, -9, 1 minus lambda. It's going to give us a lambda squared plus 9, and that means we want to solve lambda squared plus 9 is 0. Lambda will be plus or minus 3i. So as advertised, we've got complex lambdas. Step 2 is to solve a minus lambda I times v for v. We want to solve this homogeneous system and get non-trivial solutions. So when lambda is 3i, what we need to solve is -3i, -9, 0, 1, 3i, and 0. If we go ahead and rewrite this, do a row swap, what we'll find is that if we take 3i times equation 1 and add it to 2, this will become the new equation 2. If we really are going to have non-trivial solutions, we have to have a duplicate row. That's exactly what happens here. C1 will be -3i, C2. And so the solution to this system is going to be C2 as a weight in the front, -3i, and 1. So we will take this thing here to be our constant vector v1. So x1 will be e to the 3it times -3i and 1. Now, by the same token, if we were to take lambda is -3i, we would have to solve the similar sort of system. We'd get 3i positive and a -9, and we would get 1 minus 3i, 0, 0. Again, row swap to put the 1 in the top pivot. What we would find is that if we are going to have non-trivial solutions, one of those rows must be a duplicate of the other. This relationship up here is going to tell us that C1 is 3i of C2. The solution, the non-trivial solution to this problem will be 3i and 1. So we'll take this vector here to be our second constant vector, 3i and 1. So now let's compare what we found. We found that one of these solutions was e to the 3it with the vector -3i and 1. And we've just found that the second solution is e to the -3it, 3i and 1. What you'll notice is that these vectors are complex conjugates. In the same way that the lambdas were complex conjugates. Now, the lambdas we are expecting to be complex conjugates, but do we expect these v's to be complex conjugates? Now, from before, we know that if you have a characteristic equation, this is an algebra property, if you have a characteristic equation P, it's a polynomial equation in lambda that's equal to 0. If it has a solution, lambda is a plus alpha plus I beta, you can prove that lambda alpha minus I beta will also be a solution. And we've seen that before. All lambdas come in complex conjugate pairs. And that's a property of polynomial equations with real coefficients. A similar thing is going to happen when we talk about solving this thing. So when we solve the system A minus lambda IV is 0, A and I and V, they all have real entries. That's the only type of entry they have. They all have real valued entries. And so the only thing that's allowed to be complex here is the lambda. If, oops, sorry about this. If, no, I'm having trouble. I apologize here. If the lambda V pair solves the system above, we are going to take that entire equation and we're going to take its complex conjugate. The bar denotes complex conjugate. By properties of complex conjugate, that means you can essentially distribute everything. And because these terms are all real, they are equal to their complex conjugates. So you'll get A times conjugate I, lambda I, conjugate, or sorry, I shouldn't say that the V has complex is real. It is not. The A there and the V has complex entries. Sorry about that. What ends up happening is that you will have this as a pair. So the complex conjugate pair also solves the DE, or also solves the system. So the point of all of this, the lambdas and these vectors that go along with them always come in conjugate pairs. Now, in our example, we found that lambda was plus or minus 3i, and we found that these vectors, one of the vectors was negative 3i and 1, the other vector was 3i and 1. You could always view this as a real part and an imaginary part. And you could see that in this particular case, all that changes is the sign in front of the complex conjugate part. So why do we care about all of this? What's the point? We want to try to figure out what the fundamental set is. And what's going to happen, much like in the other case of scalar equations, our goal is to write them in terms of real valued functions. We have complex exponentials that we want to get rid of. And that means we are going to use the Euler formula. Now, note, if I have a solution, so if I have a solution, x of t, and it has a real part and an imaginary part, and if they're both vectors, if this x of t solves my linear system, then here's what you can do. If I were to plug all of this in, I'd have u prime plus I v prime has to be equal to a u plus iv. And so what ends up happening is that if I equate the real and imaginary parts, I end up with this. U prime equals au and v prime equals av. And that means that the real and the imaginary parts also solve the system. And that gives us a theorem. If my solution has a real and an imaginary part, then the real and an imaginary parts solve the system as well. So what we are going to do is we are going to take either one of them. So if we have the first complex solution, which was e to the I 3it times this vector, we're going to use the Euler formula, and we're going to multiply things through. And when we do this, we'll get negative 3i cos 3t plus 3 sine 3t. Sorry, I'm double checking that I have the correct vector here. Yes, I do. And in the bottom, we'll get a cosine of 3t plus I sine of 3t. I'm going to split this up into a real part, 3 sine 3t, cosine of 3t, and an imaginary part, negative 3 cos 3t, sine of 3t. This is the real part. I'm going to call it u. This is the imaginary part. I'm going to call it v. So u and v each solve the system. Are they a fundamental set? Well, what I need to do is check the determinant of the matrix that I get by plugging them in. And when I plug that in, it's a simple matter. You're going to use Pythagorean identity. And what you'll find is that you'll get 3 sine squared 3t plus 3 cos squared 3t. It equals 3, which is not 0. And it is a fundamental set. So the general solution is going to be C1 times that first times that vector u plus C2 times that vector v. So it'll be C1, 3 sine 3t cos 3t plus C2 times negative 3 cos 3t sine 3t. And that illustrates the process to you. Now, in general, when you solve for the lambda complex, you're going to get lambda is plus or minus I beta. You're going to get your eigenvectors, and they're going to be some a plus ib. You're going to form your solution. It'll be e to the lambda t, e to the I beta t times this a plus ib. You're going to find the real and the imaginary parts. Sorry, we'll call that w up there. The real part will be u, the imaginary part will be w, and you can show that this will be a fundamental set. Now, generally, u is going to be some e to the alpha t, some combination of coses and sines, and the same thing will happen with the v's. Some combination of coses and sines. They will always form a fundamental set. So I'm stating this without proof, but it will always be the case that that's the fundamental set. The same process works whether it's lambda is real or complex.